Faye Venkat, and a massive welcome to all your 7 Standard friends and classmates joining us today. I know you guys have that big science exam coming up. And look, as your teacher, I want to make sure you are absolutely 100% ready to crush it. So today, we're taking those textbook pages for Chapter 6 and turning them into guaranteed marks. We're going to lock this information right into your brains using this explainer, so when you sit down for that test, you'll know exactly what to do.
And I really mean this. We aren't just memorizing, Venkat. We are mastering. By the end of our time together today, you're going to understand the why and the how behind temperature, heat, and even some pretty cool kitchen chemistry. You'll see how it all just fits together perfectly. So, here's our game plan. 1. Measuring hot and cold. 2. How heat travels. 3. Real-world heat secrets. 4. Nailing temperature numericals. 5. Acids, bases, and pH. And finally 6. The bouncy egg experiment.
Okay, let's jump right in. Section 1. Measuring hot and cold.
Now you might think heat and temperature are the same thing, right? Actually, scratch that. They are totally different, and you absolutely need to know the distinction for your objective questions. Heat energy is measured in joules or calories. Temperature, on the other hand, is just the measure of the degree of hotness or coldness of a body, and we measure that on temperature scales. Think back to that textbook experiment with the 3 glasses of water: hot, room temperature, and ice cold. When you move your fingers from the extreme temperatures into the room temperature water, one feels hot and the other feels cold. It's wild, but it brilliantly proves that the terms hot and cold are completely relative.
Let's talk about the temperature scales themselves. On the Celsius scale, the melting point of ice is 0 degrees, and the boiling point of water is 100 degrees, neatly divided into 100 degrees, right? But check out the Fahrenheit scale. The melting point of ice is 32 degrees Fahrenheit, and the boiling point is 212 degrees. The absolute crucial point here for your true or false section is that the Fahrenheit scale is divided into exactly 180 degrees between those 2 points. Literally, lock that number in your head right now. 180?
Next up, the tools of the trade. Thermometers. If you get a comparison question on these, here are your magic exam keywords. For the Mercury Clinical Thermometer, remember it uses a silvery gray liquid and it's got a little kink near the bulb. Why the kink? Simply to prevent the mercury from flowing back down before you can actually read the temperature. Now, why might we use an alcohol thermometer instead? Well, alcohol can measure way lower temperatures. We're talking all the way down to a freezing minus 115 degrees Celsius. Plus, it's cheaper and way less harmful.
Moving right along, Section 2, How Heat Travels. So, there are 3 core modes of heat transfer, and you've got to know the conditions for each. First is conduction. This is mostly a solids thing. Heat flows from a hot body to a cold body by conduction only when they are in direct physical contact. Second, we've got convection, which is all about liquids and gases. This is actually the amazing process responsible for sea breezes and land breezes. Hot fluids rise up, cold fluids sink down. And third is radiation. This is how the heat from the sun reaches us here on Earth. It travels via electromagnetic waves, which means, get this, it doesn't even need a medium to travel through. It can travel right through the vacuum of space.
All right, on to Section 3, Real-World Heat Secrets.
Okay, Venkat, pay super close attention here because examiners absolutely love these why questions. Why do you feel warmer wearing 2 or 3 thin sweaters rather than just one massive thick one? Well, it's all about the power of trapped air. Wool itself is a bad conductor of heat, sure, but when you layer multiple thin sweaters, you literally trap layers of air between them. And air is a fantastic insulator. It creates this invisible barrier that stops your body heat from escaping into the cold outside. More trapped air simply means better insulation. And hey, this exact same concept explains another natural phenomenon. Why lakes don't freeze completely solid in the winter? When the temperature plummets, the surface of the lake freezes. But ice is actually a poor conductor of heat. It's an insulator. So that top layer of ice basically acts like a giant, thick blanket, preventing any further heat loss from the water below it. This keeps the water underneath liquid, which completely saves all the fish in aquatic life. Nature's pretty clever, isn't it?
Now listen up, because this right here is your ultimate cheat sheet for what is almost always a 3-mark question. How does a thermos flask work? A thermos minimizes heat loss through all 3 of those modes we just talked about. First, it uses insulating materials, like plastic or cork, to reduce heat flow by conduction. Second, it has a literal vacuum between its double walls. This completely shuts down heat transfer by convection, because remember, convection needs liquids or gases to work. Third, the reflective silvered surfaces bounce heat radiation right back into the flask, minimizing loss by radiation. Write those 3 exact steps down, and boom, maximum marks.
Next up, Section 4, Nailing Temperature Numericals. I know some students tend to panic a bit when they see math pop up in a science test, but Venkat, I know you're going to totally nail this. Formula alert, you just need to etch these two formulas into your memory. To find Fahrenheit from Celsius, the formula is F equals C times 9/5 plus 32. To go the other way and find Celsius from Fahrenheit, the formula is C equals 5 times the result of F minus 32, all divided by 9. Let's look at how this actually works in practice.
Let's plug in some real numbers from your textbook exercises. If we start with 110 degrees Celsius, we multiply that by 9/5, then add 32. Boom, 230 degrees Fahrenheit. Easy. Now let's reverse it. Take 131 degrees Fahrenheit, subtract 32, multiply by 5, divide by 9, and you land perfectly on 55 degrees Celsius. Try to visually memorize these specific final answers so you can double-check your math on test day. It's an easy points grab.
Moving on to Section 5, Acids, Bases, and pH.
All right, let's organize that messy chemical data from your chemistry worksheet too. First, remember the golden rule. Acids turn blue litmus red and bases turn red litmus blue, period. Now let's map this out. Substance F is sulfuric acid. It has a pH of 2, which makes it a really strong acid. Contrast that with substance A, acetic acid. It has a pH of 6, so it's a weak acid. On the flip side of the scale, we have substance D, sodium hydroxide. This is a solid with a pH of 12, so that's a strong base. And what about substance B, common salt, or substance C, which is water? Well, they are perfectly neutral. They have a pH of exactly 7 and will have absolutely zero effect on your litmus paper. If you can just picture this table in your head, you are going to sort those chemicals effortlessly during the exam.
And finally, Section 6, the bouncy egg experiment.
Okay, if the test asks you to compare the physical state of the egg in this experiment, here is exactly what you need to write. Before the reaction, the egg obviously has a hard, rigid shell, and the insides are completely hidden. But after it sits in the vinegar for a while, the shell is just gone. The egg becomes soft, flexible, and completely rubbery, and you can actually see the contents inside right through the thin inner membrane. That membrane is permeable, and importantly, it doesn't get attacked by the acid.
So what is actually happening chemically here? Well, vinegar contains a weak acid called acetic acid. The eggshell itself is made of a base called calcium carbonate. When those two meet, we get an acid-carbonate reaction. The acetic acid reacts with the calcium carbonate to form a soluble salt called calcium acetate, plus water, and crucially, it releases carbon dioxide gas as tiny bubbles. That chemical reaction is what literally dissolves the rigid shell away.
But wait a second, how do we actually know the gas bubbling up is carbon dioxide? I want you to really think about this, Venkat. What is the definitive chemistry test we use to prove this?
Yes, you pass the gas through lime water. If it truly is carbon dioxide, it will turn that lime water milky. Locking in that final piece of knowledge is going to guarantee you maximum marks if this experiment pops up. Examiners love asking for that proof, so don't forget it.
And just like that, we've covered all the core concepts from Chapter 6. You guys did it. But before we wrap up, I want to leave you with this thought. If a simple, weak acid like the vinegar just sitting in your pantry can completely dissolve a hard eggshell and turn it bouncy, what other chemical mysteries are hiding right there in your kitchen, just waiting to be explained? Science isn't just trapped inside your textbook, it's literally all around you. Venkat, you are incredibly well prepared for this exam now. Make sure you share this explainer with all your classmates so everyone can walk into that exam room completely confident and ready to conquer this test together. Until next time, keep observing, keep asking questions, and keep mastering.